Thank you, Zach. Thank you. And big thank you to everybody at Passive House Accelerator for like embracing this story and letting us share it tonight, but really mostly for all the work you've done these 2.5 years. It's just really, really, really fantastic. So um, because there's so much to deliver here, and you, those of you who know me know I can speak at great length about this stuff, maybe too much, that I actually wrote it down. So for the first time in ages, I'm actually going to read from a script. So sorry about that, but I'll do my best. So, all right, I'm here to start with a short story before Zach and Skylar take us all to the core of the matter. But I want to open with a question to you all. Who's ever been confronted with the concept that we here in the Passive House world are going too far? Let me see a show of hand from folks who've developed a set of talking points as to why we bother with the work we do. Who's yeah, right? Really common. You go too far, right? All right. I'm finding it's no longer a point to rise to, but I know I don't want to build a code building or even a pretty good house. I want to create a very good one. If they want to stop short of the engineered calculated balance we spend a little time assessing, it's their loss as well as the Earth's. But another question, who has been confronted with the concept that we are going too far towards efficiency? It's that we're actually doing more harm than good by bothering with our extra efforts. Yet the extra time, materials, finances, and care we invest in our optimized low-load buildings is not only a waste, it's effectively accelerating the demise of our climate balance, that we're driving more nails into the coffin. Who here's run across that one? Anybody? All right. So I know I have, and it's disconcerting to be confronted with this concept since I've dedicated a lot for decades to this effort, mitigating humans' negative impact on our planet by delivering better buildings. If I'm doing this wrong, I want to know how to correct my efforts. So I just crossed the year 35 in the construction field, and I'm moving back into building buildings, having focused on consulting for others for the past 5 years. But now it's time for me to put money on the barrel and to build some buildings. And I've heard that I'm doing it wrong from someone I respect but didn't agree with. And luckily, I have had a fantastic opportunity to work with, but mostly to get to share thoughts with and life's path with some terrifically smart people. So I turn to those two, they're on your screen, Skylar and Zach, with this question. What is up with this embodied carbon conflict with operational carbon? And happily, we're an amazingly sharp community that wants to get to the root of the issues. And Skylar is one of the sharpest out there. And I need to apologize as he spent untold hours now diving in so deep that the 1 a.m. texts seem to be coming continuously. But what he's assembled in both background science and engineering, as well as his assessment tool, are a marvelous aggregation of information which we can use effectively to build a better world. So without further ado, I would like to raise a toast to all of you who, when faced with a challenging condition, you get to work and create beautiful solutions. They may be nerdy solutions, but they're beautiful. So cheers to you all. Thanks everybody for being here. Nice big crowd. It's terrific. So I just want to, I don't think I need to introduce Zack Semke, but I will. He's the guru of marketing. Really the guru of messaging. So Zach has fantastic capacities to message, and I got the opportunity, as he said, work with him and see what he could create. So such a great message creator and communicator. But then Skylar Swinford, who some of you know, many of you, if you haven't met him before, he is one of the friendliest individuals out there, and buy him a beer because he will want to share his insights with you directly because he's just a friendly individual. He's based out of Boise, Idaho, and he told stories of his father making him carry insulation bundles of cellulose up steep stairs when he was not even a teenager yet. So he comes from the air sealing, insulation, and ventilation world. He was born and raised in that. And he's brought that experience forward in running that insulation, air sealing, and ventilation company there in Boise, and also delivering fantastic background knowledge and consulting through his company, ESCO. So one of the premier energy modelers and passive house practitioners, I would say, in the world personally, but I don't get very far out in the world as much as he does. So great people, sit back, get ready to hear fantastic things from this dynamic duo.
Thank you, Dan. I am so honored to be able to tee up this conversation and provide just a little bit of context to the insights that you're about to hear from Skylar and the information you're about to get from him. And I want to do it as quickly as possible because it's important that we get to that as fast as we can. So I just want to share some of the insights that his work and will be showing. So here is a quick overview. One is we're going to be talking about the fact that passive house and embodied carbon reduction are not trade-offs. That's the numbers are showing that that's not the case. We're not talking about balancing or compensating for one or the other. They are not trade-offs. Instead, passive house reduces a building's total emissions. So that's both embodied carbon and operational carbon emissions, even by 2030. In fact, even if we set the horizon just out a year or two, as you'll see in the numbers, while also decarbonizing winter heating peaks. And that choosing low embodied carbon materials also reduces emissions. So let's do both. And in this conversation, we want to emphasize that all four of these things that you see here, passive house efficiency, carbon sequestering materials, electrifying everything, clean energy, all four of those are vitally important, and they need to ramp up as fast as possible. And we're kind of supporters and cheerleaders of all four elements that will lead toward zero carbon building. We're also finding some climate progress, maybe even some accelerating progress in the United States. The Inflation Reduction Act surprisingly passed, and the three separate modeling groups see that as bringing us to 80% of the way toward our 2030 target of decarbonization in the United States, which is striking distance to doing our part toward a 1.5 degrees Celsius warming future. But that is not going to be easy. In fact, this task in the United States will require us from now to 2050 to double the amount of electricity generation happening in 2050 as it is happening now, all while subtracting all the fossil fuel generation from that energy grid. So there will be NIMBYism that will try to slow it down. There's going to be permitting problems, and we need to address that. And this is going to be tough. And so we want to make that as easy as possible. In the perfect world, we would see totally nice and flat loads on the electricity grid, not fluctuating during the year. Because when we see a peak in load, that means we have to overbuild the generating capacity in order to meet that. And that makes the task even harder. So and we know that buildings play a critically important role in all of this, because as you can see, that crazy line there, this is from Saul Griffith, and what he's looking at is electricity use in the US now, and what would happen if everything were electrified. So if we electrified all of the natural gas burning and oil burning that is happening in buildings, we would have these huge spikes in electricity use during the wintertime. Of course, and that's because of heating demand. So in Passive House, of course, we know how to address that. This issue is becoming more and more front of mind and discussed in academic circles and beyond. And this is a paper that came from Nature magazine this year. It says inefficient building electrification will require massive build out of renewable energy and seasonal energy storage. And in it, they say, we found that US monthly average total building energy consumption varies by a factor of 1.6 times. So lowest in May and highest in January, so winter peak. This is largely managed by fossil fuel systems with long-term storage capacity. Meeting this peak with renewables, which is our project, would require a 28 times increase in January wind generation, or a 303 times increase in January solar, with excess generation in other months. Highly efficient building electrification can shrink this winter peak, requiring just 4.5 times more generation from wind and 36 times more from solar. Those are still big numbers, but we're talking about a roughly order of magnitude smaller task if we are serious about building energy efficiency. So they go on and show this curve, which is now known as the falcon curve because it looks like the wing of a falcon as it's flying toward you. And what we're looking at is on that green blob on the bottom is existing electricity demand from the residential sector. Then we see industrial, direct use, and commercial. Those are the blobs of color. And then the lines show different scenarios of electrification and building energy efficiency. This is simplified in this study to look at the efficiency of the heating systems in these buildings. So that's why you're seeing the COP, the coefficient of performance of the heating. And it ranges from that really scary, the wings straight up of if we were to electrify everything, all the heating, and heat with direct resistance heating, which is a COP of 1. And that shows massive peaks that would be very difficult to meet with clean energy. That beautiful dotted purple line that you see, or magenta line that's at the bottom, is what would happen at a COP of 6, which is practically not possible right now with heat pumps, but a COP of 3 is. And if you combine the COP of 3 heat pump with passive house, then you can get to that much flatter, clean energy grid friendly reality. And that's what we want to do. But what about embodied carbon? So I want to outline 3 key common assumptions about embodied carbon and building decarbonization. And how we're going to, you'll see the numbers push back on that when Skylar presents. So first, the common assumption is that building energy efficiency means higher embodied carbon and often higher overall emissions. And the notion is that something like passive house, as Dan was mentioning, could be counterproductive. So that's the first assumption. The second is that the time value of carbon dictates that 2030 is the important time horizon, not 2050. And this notion of the time value of carbon is a really important one. And that is that we want to avoid short-term big carbon emissions burps now, because if we emit a bunch of carbon now early on, it has a long time during 2030 and all these really important decades during this time of climate crisis this century to make the problem worse. So we want to avoid those burps of upfront carbon, and so that's it's an important concept. Third is this notion that if my utility's electricity is near zero emissions, then building energy use isn't that important anyway, right? Because if my utility's electricity is near zero emissions, I'm getting clean electrons, and if they're not carbon, if there are no carbon in those electrons, then who cares if I burn them or use them? Okay, so let's take these one by one. First, we rightly, as a community, are addressing that first one by looking for low embodied carbon and carbon sequestering materials that can support our highly energy efficient building designs. That is an important and smart thing to do. But we can take a step further and ask the question, when you're assuming that energy efficiency means higher embodied carbon, are you accounting for the fact, or are you accounting for the smaller embodied carbon and the smaller refrigerant leaks from the smaller systems in a low load building? And if you aren't, you need to, because this is a vitally critical question, and you're going to see a lot about that, I think, in Skylar's work. Okay, so then the time value of the carbon is an important concept. Let's also acknowledge that moving the horizon up from 2050 to 2030 also is something of an accounting trick, right? Because it elevates the importance of embodied carbon and discounts the ongoing importance of operational carbon emissions. So while there's truth in the time value of carbon, let's be honest that there is a bit of an accounting trick going on here. But even more importantly, we need to also look at the time value of efficiency. And that is the reality that, yes, we are part of it. We're in the early stages of a clean energy transition, but we're far from there yet. And regardless of point number 3, the reality is that even in a city like Seattle, we're getting dirty electrons. We have carbon rich electricity right now. And that'll change over time, and we'll get to a place where we're near carbon-free electricity, but we're not there yet. So in this critical decade of 2030 and ensuing years, we should be prioritizing energy efficiency, because when we are energy efficient in operational carbon or operationally, we are avoiding the burning of dirty fossil fuel generation for electricity. And this last point is that the pushback here is the reality that it's a mistake to magically kind of create a magical boundary around a city like Seattle. So in Seattle City Light boasts of being the nation's greenest utility. And it is true that the electricity that is generated by the dams that Seattle City Light operates are near carbon free. But we're part of a vastly larger geographic grid area in our grid called the Western Interconnection. And our electrons go elsewhere. We get electrons from other people. There's all sorts of interchange. It's like a big soup, as Skylar will talk about. So it's a mistake to pretend that our electrons are clean. And organizations like the Environmental Protection Agency, NREL, and the Union of Concerned Scientists recognize this and caution against that mistake of assuming that if you have clean electricity from your utility, that the emissions factors of your electricity are low, that you instead need to look at the region. So with that, I will stop and Skylar will take over. Thanks, Skylar.
Thank you, Zach. I appreciate that. Can you guys hear me? All right. Zach, thanks for the introduction. And thanks everyone for having me today. I'm just going to dive in and start discussing the operational and embodied carbon emissions estimator tool that I developed to address this very problem that Zach presented. This is a screen showing this tool, and really what I've done with this tool is, I'm sure as any other Passive House consultant can relate to, over the years with different projects I've consulted on, I've developed like 20 different spreadsheets that have a calculation for embodied emissions and different graphs and different outputs. And my goal was to bring this all together into one tool. And just to show the importance of it, just to lead off where Zach left off, is the very first input in this tool is the emission factor. And I'm going to spend some time after I just kind of quickly go through some of the inputs in this tool, really diving into the emission factors and where they come from and what to be cautious for, and how to really kind of maybe spot how some other practitioners may be misapplying emission factors to discount energy efficiency and the operational benefit, operational emissions reductions. So in this tool, you can compare two cases, and there's a way with zip code, you can look up your eGrid subregion that you're located in, which I'll get into in a little more here. And then you can put the area of the building, the EUI input. You can compare an electric building with a gas building, and you can compare different heat pump capacities, different refrigerant types, different leakage rates, different time frames for how long the equipment will last, if the equipment is actually topped off with refrigerant, if there's an assumed leak, and look at different COP impacts. We also are able to input if the project has PV. You can look at the embodied emissions of the PV system, the embodied emissions of the battery system, if you have some storage on site. And then also one part of the tool that's really cool is a lot of this tool actually was inspired by the amazing beam estimator tool. And what I wanted was just to have a single tool where I could have operational energy in there, in the tool, and then also be able to compare a building with triple pane windows versus double pane windows, or with different insulation types. So this is like a mini beam calculator that uses the beam, all the insulation types in beam right here, for easy comparison. And then you can also take outputs from other third-party tools and use those in some of the visualizations that are generated in the tool. Here's an example showing some different outputs where not only are the upfront emissions for the structure put in place, for example, from the beam tool in this light gray, you can also compare the leakage rates based on the HVAC system, the PV systems, and also enclosure upgrades. If you want to look right in this tool and kind of see, hey, if I wrap this building in mineral wool, or if I did cellulose, what would how would that impact my two cases? And then the part of the tool which I spent the most time kind of grasping was incorporating future emission scenarios into the projections for the accumulated operating emissions of the building. So you can actually look at two cases across a range of future decarbonation scenarios and really see how the building will perform, not only with retrospective emissions of what emissions were yesterday for the grid and today for the grid, but what they may actually, how the building may perform long-term with different emission factors and how that impacts the long-term emissions of the building. The graph also plots out refrigerant emissions and the embodied carbon as well, just for a visualization. And all this is additive. And unfortunately, we're not going to have enough time for me to dive into the tool during this presentation. But during the Q&A, I'm going to actually get into the tool, and hopefully I can answer some of your questions there that arise, or some what if scenarios about, hey, what if we wrap this building in X insulation type? How does that impact the upfront emissions of the building? Now, kind of diving away from the tool itself, I want to get into really where I dove deep in some of the assumptions for the tool, and that's with respect to the operational emissions and the emissions factors. And that's why I really thought it was important to incorporate kind of the best practice emission factors in this tool. I'm just going to say one of the biggest issues I see my peers doing that present operational emissions data is really using the wrong geographic boundary for their emissions calculations. And really the biggest issue is when you use too small of a region, it can neglect imports and exports, but it also will ignore the interdependencies of supply and demand in larger geographic regions beyond utility and state boundaries. So this map here was presented by Graham Finch in a recent presentation, and you can clearly see there's distinct boundaries of the emissions, but in reality, the grid extends beyond these political or geographic boundaries, and we need to look at the bigger picture of the grid. Here's a map showing emission factors for different states from the EPA eGrid, which is really one of the best sources for emission factor data. And here it's organized by state, and I'm going to be using the Northwest Power Pool and the Washington State in a lot of my examples, because that's where I work on a lot of projects. And you can see if you just use that state boundary of Washington, you would think that you have a very low emission factor for the project. Even though the average in the US is 800 pounds per megawatt, Washington's about 4 times less than that at about 200 pounds per megawatt hour. But if you look into the documentation for the eGrid, and you look into the documentation from other entities that do emission factor calculations, like whether Zach mentioned the Union of Concerned Scientists, DOE, NREL, all these different entities, they really encourage using the subregion, because subregions, unlike states, are defined by the transmission, distribution, and utility service territory of power plants, and therefore don't follow traditional geographic state boundaries. On this image to the left, you'll see kind of the major interconnects of the kind of regions and balancing authorities, and each of those white dots is a balancing authority that's responsible for an area within a region. And it's just really important to demonstrate that the grid does not follow traditional geographic or political state boundaries. It's highly interwoven, highly interconnected. In the WECC alone, there's over 130,000 miles of interconnected transmission line. And the grid works like a single large machine that's highly interconnected. And it's interconnecting distant areas with these transmission lines. And the electric current on these transmission lines are transmitted at the speed of light as physics dictates, and they don't obey political boundaries. NREL recently released some documentation on greenhouse gas emissions counting in buildings, and they also implored users. They say the most common regional values are based on the 26 eGrid subgrid regions defined by the EPA. State level emission factors may not be a good representation of local emissions and are not recommended. So if I were trying to do a calculation for operational emissions for a project in Washington State, I may just go to the eGrid online tool and pull up this emission factor of 200 pounds per megawatt hour. But if I were to zoom out and look at the whole Northwest Power Pool region, I would see that the emission rate is actually 3 times the state rate. And this is a more accurate description of the regional mix. And so it's 3 times that 200 pound rate. And then also in the WECC, for reference, which is a larger region, it increases to about 700 pounds. And so even if you get the region right and you use the NWPP, one thing that these values are ignoring, which are important to consider, is upstream emissions and also transmission losses are not. And so I've seen people use the right regional number instead of using a state or utility, but then they aren't accounting for any of the upstream emissions related to that energy use. But luckily, ASHRAE 189 has specifically calculated emissions factor for each region based on the mix of fossil fuels in that region. And they've provided corrected values. These are the same values that are also listed in the IGCC 2021. So if you reference that document, you can see that the NWPP, when you account for upstream emissions from whether that's methane leakage or extraction of coal or transport of coal, it bumps the value from 936 pounds per megawatt hour to from 600 to 936 pounds per megawatt hour. And I'm just going to make a quick note because we're short on time, but the emissions factors often used for natural gas, they're adjusted in here as well to account for leakage. And that is about the upstream adjustments for natural gas equate to about 40% more emissions for natural gas combustion than you would typically see calculated if you just use the combustion on site. And this is just to visualize. The dark blue lines are the corrected emission factors for upstream leakage. And the lighter blue is the eGrid value, and there's about a 55% emissions increase. So if you were doing a calculation for your project, you could have a real large range of results. One from, if you use Seattle, pixie dust, fairy values of 0, you could have just like, there's no point of efficiency from a operational emission saving perspective. Or you could use the eGrid values for Washington State, or you could use the more accurate values that account for the upstream emissions. And so you could be off by a factor of 4 or 5. So just be really cautious when you're using emissions factors and really dig into some of the assumptions people are using, because unfortunately, a lot of cases that I've seen, they're using really ultra low cherry picked values for places that aren't really representative of the regional grid. One last concept I'm just going to dive into is the concept of marginal emissions. And all the values that I've currently presented are average emissions, which would be like if you took the emissions rate of all the generation and you averaged it out. And so even though you have some coal over here and you have some renewables down here, your kind of average rate might be in this range. But in reality, we know that in a competitive electricity market, renewables and things like nuclear, they're running pretty much max output all the time. And so a lot of what we're seeing when we increase our electricity demand to electrify is, unfortunately, we're moving the needle this way to a lot of marginal resources. And even though on paper and an accounting perspective, we can claim that the building has low average emissions, but in reality, if you looked at how the building influenced the grid or a new electrical load influenced the grid, unfortunately, in the short term, there's a lot of high emissions coming from more expensive fossil fuel generators on the margin. And so if you want to get context for that, you can look here for Washington State. The eGrid publishes a non-baseload output emission rate for Washington of nearly 1,300 pounds per megawatt hour. And so that's like under peak load conditions, what you'd expect kind of the emission rate to be, which is 7 times higher almost than their standard emission rate. And this is just to give you context. And I'm just going to say, I do not use short-term emission rates in calculations. I would also be very skeptical of any calculations that use them, because oftentimes they're used by kind of bad actors that are trying to argue against electrification and trying to say that electrical emissions are so high, we should continue with internal combustion engines and we shouldn't use EVs. But in reality, as we decarbonize the grid, that marginal emission will come down as we add new generation to the mix. And that's where the real beauty and really the gold standard of emissions are what are called forward-looking or long-run emission rates. So these are marginal emission rates, but they account for how the grid is impacted by not only electrical load growth, but also decarbonization of the grid. So it looks at current policies and future policies and cost of electricity and how the grid is going to transform. And you can actually get a range of scenarios, just similar to how you would see with a climate model where there'd be a range of outcomes. The NREL Cambium tool is able to produce these long-run marginal emissions that you can use to assess your building on a longer time frame out to 2050. And then just to hammer home, I took a screenshot of this earlier today, and I just want to zoom in here on BC exporting about 330 megawatt hours to Alberta, and that if BC had a policy where they increased electrification, they were no longer able to export that hydroelectricity to Alberta, then you no longer would be offsetting this 450 gram carbon intensity electricity anymore. So things that happen in one region have an impact on another region and the emissions in another region. And we have to think in systems, and that's how Passive House consultants are trained, is to think of the building as a system and to think of these things in a broader sense. Hey, Zach, how are we doing on time? Could I take another 5 minutes?
Yeah, go, Skylar. Don't stop.
Okay. So basically, I'm just going to kind of go through how the tool is structured with some examples before we actually dive into the tool. But basically, the foundation of the tool is to understand what the building EUI is. And so you can get that from the PHP or a WUFI model. And basically, it's the total energy use divided by the floor area in kBTU per square foot per year. Sorry for those that are on SI. I'm going to be mostly in inch pound here. But this just shows, even in Seattle, which is in the NWPP, where you have about a pound of CO2 equivalent emissions per kilowatt hour, cutting the EUI from 30 to 15. And I've seen single family passive house projects that are EUIs are less than 10. But I'm just using this as an example. You can easily cut 8,000 pounds of CO2 emissions per year. So this is one of the cleanest regions in North America. To say that there's not opportunity for efficiency to reduce carbon is really misleading and not really informative. And beyond that, a lot of analyses completely ignore the HVAC reduction that comes with a passive house. So if you model the project, a 2,000 square foot house with kind of a code enclosure, you could expect anywhere from like a 3 to 5 ton heat pump that would be required. And where the passive house, my passive house in Boise, Idaho, for example, is which has a design temperature like in the single digits in Fahrenheit. It has a 1 ton heat pump is all it has. So that load reduction has a big impact, not only on the equipment itself. So the equipment being almost 3 times smaller can have a third of the upfront emissions just by the equipment being smaller, but more importantly is on the refrigerant side, especially with standard air-to-air heat pumps that we're seeing on a lot of projects still. And I know we're pushing to move away from R410A, but this is a pretty standard on single family and smaller multifamily projects, and multifamily projects with VRF is a lot of 410A. And the emissions from just 13 pounds of R410A on a project is just massive difference, like 30,000 pounds of emissions potentially if that refrigerant were to leak versus 7,500 pounds with the smaller system. So the smaller equipment sizing can't be understated how important that is, especially with high GWP refrigerant. And in the calculator, you can select different types of refrigerant to see the impact and the benefits of that. And I know many of us are working to use lower GWP refrigerant, but this is just for an example. Another piece that I often see ignored in the conversation of upfront emission is the size of the PV system. For the tool, all you need to know is what 1 kW. So if you install 1,000 watts of PV on the roof, you just need to go into PV watts and put a 1 kW system in, and it'll tell you based on your roof pitch about how much electricity that system will generate over the course of the year. In Seattle, I'm just going to use 1,000 per kilowatt hour because it just makes the math easier. So if you have a project with an EUI of 30 and you have a project with EUI of 15, the PV system goes from 17.6 kW to 8.8 kW if you are trying to offset all your electricity use on site. And if we assume 615 grams of CO2, or 615 kilograms of CO2 per kW, that's about a 10,000 pound emission difference in the PV system alone. But I just want to be really clear on my projects. Even if we do an ultra efficient passive house and we have extra roof area, we try to max out the PV, because if you take that 1 kW of PV, it's really important to keep this in context, because when you're looking at the upfront emissions for a project, the PV may look like a lot of carbon, but it's producing a lot of electricity. And when you take that 615 kilograms and you divide it by the 20,000 kilowatt hours of production that you may get from your system over 20 years, that electricity comes out to very low carbon of 31 grams of CO2 equivalent per kilowatt hour. And compare that to the Northwest Power Pool, which is one of the cleanest in the region. And this is the average emission. It's not even a marginal emission rate. And it's 425. And then on the right here, I just, from Wikipedia, there's some life cycle emissions from different sources of electricity. And solar PV, you can see, even if you use panels from China that were made with coal electricity, you might triple or double the emissions from this, but it's still very low compared to natural gas and coal. And so it's really important to keep context and perspective, and to look at things like from how they compare to what a future renewable grid would be, and don't just look at them in isolation. And I'm just going to close here before we head to the Q&A. The kind of the backbone of the tool is using these different emissions forecasts and scenarios. So here, just to put context, coal is about 1,000 kilograms per megawatt hour of emissions. Gas in the Northwest is down here at about a little over 400 kilograms of CO2 per megawatt hour. And then the Cambium forecasts are able to streamline this wedge of emissions is 95% decarbonization out to 2035, and then 95% at 2035, and then this silver line are emission rates, emission factors going out to 2050, and then kind of in the middle here is just a range of scenarios that you could have, and so it's just kind of the error bars depending on different cases of renewable costs that are forecasted out. And then basically, I think we're going to hop to the Q&A, and then I'm going to dive into the tool, and I can answer some of your questions with that tool to do some what if and scenarios, and I can show basically what building emissions are looking like versus operational emissions on different time horizons, and kind of give you some context.